All right, so last time we saw some of the fundamentals of creating a linked list. We saw how to make a class, how to get the size, what a node means, what the head reference is, and stuff like that. We also did the insertAtHead, which is the easiest way to insert into a linked list. And today we're going to start with the removeAtHead, and then we'll move on to the insertAt and removeAt methods, which are a lot more complicated but very fundamentally important. So starting with the removeAtHead, let's talk about that very briefly, and then we'll go ahead and write it. First of all, if you're going to remove an element from the head of a linked list, all you have to do is get the head reference to point to the second element in the linked list, and then it will dereference the first element. Or if the list is empty, you of course don't want to do anything. And then also, if the only element in the list is the head node, then you want that node to be gone and the head reference to be set to null. So what we have is what we had before. We have our head reference, and it will be pointing at a node, right? And this node will be pointing at, we don't know. It could be pointing at nothing, meaning it's null, or it could be pointing at something, meaning that it's not null. And the assumption when a next pointer is not null is that it's looking at a node. So what we can do very simply is get the head reference to be equal to this, and whatever it is, that will be correct, and this node will be bypassed and therefore removed from the list. So I'm going to switch to our code and actually type this. All right. And so here we have our insertAtHead, which we did last time. And so now we're just going to do its sort of companion, removeAtHead, which is fortunately also very easy. So we'll make this public. And in this case, there is the chance that the removeAtHead will fail. If there are no elements in the list, then you cannot remove from the head of the list because there's nothing there. Unlike the insertAtHead, the only way that could fail is if you ran out of RAM. And as we discussed, that's just too out of our realm to deal with. We don't really care. If the programmer runs the RAM out, then that's their problem and they've got to figure it out. What we're going to do here, though, is we're going to make this removeAtHead Boolean, because you can fail to remove. And what we are doing is we're just going to take the thing off. Some removeAt methods or remove methods return the value found there, but we're just going to return true or false, indicating success or failure, and leave it at that. And so we've got really a very simple set of items. Step one is the list empty? And that's very easy. And we just say if head is equal to null. If that's true, then we return false because we're done. Nothing to remove. Step two, if not, bypass the head node. Remember what the term head node means. The head reference is a reference, right? So this reference, the reference that I call head, that is not a node, it's a reference. The head node is whatever node the head reference is pointing at, because that's considered the first node in the list, so it gets the name head node. So we just want to bypass it, so we just set head equal to head.next, and we're done. We return true. And here's the thing. If the first item is true, then there isn't a node there. The moment we get to step 2, we know there's a node there. There has to be. So if there is a node there, in order to bypass it, we set the head reference equal to that node's next value, and whatever it is, head will be looking at that. So if that next node is looking at another node, then head will bypass that first node and remove it from the list. It will no longer be referenced, and the garbage collector will throw it away. But if that node is the only node in the list and its next reference is null, well, then head will set itself to null, and voila, it's already in the state we want it to be in, because if head is equal to null, the list is empty. This removeAtHead basically works itself out. There are only 2 steps. If it's empty, can't do it. If it is, we can, and it's literally 1 line of code. So the removeAtHead is fantastically simple. Let me just say this right quick. If all you have is an insertAtHead and a removeAtHead, you have a linked list that can be used to store an unknown amount of data. If you just need to dump a bunch of data into a linked list, you can just insert it at the head and it will just store a bunch of data, and you'll have exactly as much data as you need stored in a sequence. Now, it'll be in reverse sequence of what you put it in, but that doesn't really matter. You'll still have it all. And if you want to get that data back, you can get it back by removing at the head. So sometimes data is dumped into linked lists because it's a convenient, quick storage for it. Because what do you need? You need a node, you need a head pointer, and you need an insertAtHead and removeAtHead, and then you can put however much data you want if you're just literally just dumping the data in and then pulling it back out. Even now we have something that has use, even though that use is somewhat limited. So that's the removeAtHead, which I mentioned is very simple. InsertAtHead, removeAtHead, no problem. Okay. Now we're going to talk about the tricky ones. Now we're going to talk about inserting wherever you want, using a position. When you're inserting into a position in an array, things go much quicker in terms of knowing where you are, because you know that if the index is negative, then they're giving you a position that you can't insert into. And also, if they give you a position that's greater than size, then you can't insert there. And also, if the list is full, you can't insert there. Well, here's the nasty part of working with a linked list. You can tell if the index is negative, it won't work, because we're going to start our indices at 0. But you can't tell if it's too big, if it goes beyond size, without counting all the nodes. By the time you've counted the nodes, you could already be done inserting, so there's no point in counting the nodes just to see if it will fit. So what we're going to do is a real tricky thing. We're going to verify the position, but only in 2 situations. If the position is negative, we can't insert. If the position is 0, then we can insert at head, because we already have that code. But if it's anywhere else, then we've got some work to do to figure out where we are and how to insert. So let's talk about this on the board for a little bit. All right. We have our head reference, right? Our head reference is going to be pointing at a node and this node is going to be pointing at a node, and this node's going to be pointing, and let's just make a few more. Let's get about 4 in here. You make sure that that's fitting on screen. Let's get about 4 in there. All right. This is our linked list after 4 insert@at heads, whatever. And now we want to insert at a position. So the things we need to immediately worry about is whether or not the position is valid or even possibly valid. So that's our first check. If position is negative, right, then that's a fail. We can't even do that at all. There's a special case here because if the position is 0, then we're going to have to modify the head reference. This is the only position where we have to do this. So we need to treat it as a special case. So if position is 0, then we insert at head. All right. And we already know how to do that, so that's not going to be a problem. In fact, what we're going to do is just call the insert at head because we already wrote that code. In some of your assignments, you're required to not call other methods. I do that so that you'll write more code, just to make you practice more. Even if you just moving code around, I want you to work with the lines of code, with the statements more. It's better practice. Anyway, but we're going to take a slight digression, and if this is true, we're going to insert at head. Now, here's the tricky part. If we're not inserting at position 0, then we need to move to the correct position. And here's the position that we want to get to. We want to get to the node that's ahead of the position. Okay? We need to get to the node that's pointing at the position we want to insert into, because that node is going to anchor the new node. All right? So if we are inserting at position 1, which would be here, this is position 0, right, would be ahead of this node. But if we're inserting between these two nodes, then we need to get to this node, which is at position 0, so that we can modify this reference. If we're inserting at position 2, we need to get to the element at position 1, because 1 points at 2. And this is true the whole way. All right? In every situation, we need to get to the pointer that's ahead of our position. So we need to move through the linked list, just like we did with our size method and our print method, where we just literally just went next, 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 next. But we need to count where we are, and we need to stop when we get to position -1. If they want to insert into index 2, we need to get to index 1. If they want to insert at position size, this is 4, right? This is element 3, 0, 1, 2, 3. If they want to insert at the end, all we need to do is get to the last node, which is position -1. So in all cases, other than position 0, we need to just move to position -1. Now, while we're doing that, what can go wrong? Well, what if they give us a position that's too big? Well, in that case, as we move through the list, our pointer, our reference that's keeping track of where we are, will eventually run into null. It will hit the end of the list and become null. If that happens, then we know they gave us a position that is too big and we can't insert. So while we are traversing, we're trying to maneuver to position -1. If we hit null before we get to position -1, then they gave us a position that is too big, and we return false. So it's relatively complicated. So we move to position -1. And then if we hit null, then that's bad. If it's not null, then we're okay. And then if we've gone to position -1, we create a new node. I decided to wait until this point because if they gave us a bad value, there's no point in creating a new node and then not using it because they gave us a crappy value. So we'll create a new node and we'll insert it. All right. And so what I'm going to do is I'm going to start writing the code by putting these in place. And when I get to this, I'll start drawing a little bit of what I'm doing. So I'll write some of the code and then I'll draw what it